we will continue looking at problems in chromatography. Let us look at a problem. So, there is a peak that is eluting out, the maximum is observed after 470 liters of collection of liquid. Now, this is a BSA protein and the column size is 80 liters and the void fraction is 0.4. You are asked to calculate the equilibrium constant, that is the K, assuming that there is a linear relationship. Okay. So, if you remember, recall your old lecture, the equation is T naught, that is the elution time, is a function of the voidage, K, volume of the packed column, and Q, the flow rate. So, if I multiply T naught with Q, Q T naught will become the volume. Okay. So, that will become 470, epsilon, that the void fraction is given 0.4, the volume of the packed column is 80, and all you have to do is calculate K. So, simple actually. Okay. So, you just have to recall the equations, and that is what we are doing here. Okay. So, we take that equation and we multiply on the left hand side by Q, T naught Q is 80. So, when you substitute all these, so we end up with K is equal to 9.1, that is the equilibrium constant. Let us look at another problem. So, the maximum concentration that is C naught here. Okay. Now, we are reaching 3.6% of that. Okay. Calculate the number of theoretical stages. Okay. Now, you have to recall an equation which connects Cf with C naught and the number of equilibrium stages. Okay. So, that is the equation, C naught is equal to Cf square root of 2 pi n. Okay. So, the maximum concentration C naught is 3.6% of the originally that is present in the column. The originally that is present in the column is Cf, the C naught is 3.6%. So, when you do that, we bring it on the left hand side, it is 0.036. So, we can calculate n the number of theoretical stages, that comes out to be 122. So, if you recall the original set of equations, so you have some concentration Cf and then it starts going down and it reaches a distribution of this sort in the exit side. Now, let us look at the chromatography as two stirred tanks. Suppose you have a stirred tank here where you are introducing the feed and there is a product going out, and there is another tank which is not stirred, but this is connected to the first tank and there is a mass transfer taking place here. Okay. So, this is almost like a dead space and this is well mixed and product is the feed is entering here and it is going out here and there is a mass transfer taking place. Okay, here. If K can be some number between 0 to infinity, that tells you how good the mixing that is taking place in that void dead space as well as the mixed space. So, you have having a feed, the problem is you are having a feed and a pulse of C naught is given at time equal to 0. Okay. If K is equal to 0, derive an equation for the outlet concentration. If K is equal to 0, there is no mass transfer taking place. So, we can completely ignore this tank. Please remember this, we can completely ignore this tank. So, it is like a tank stirred with the volume V and you have a feed, we have a stream coming out and there is an input pulse injected with a concentration C naught at time equal to 0. You would like to know what will be the outlet. So, you have the regular mass balance here, input minus output is equal to accumulation. Okay. So, input minus output is equal to accumulation. So, when K is equal to 0, we are ignoring the entire tank 2. So, when we do that, input minus output is equal to accumulation. So, we can say input is 0, output is Q multiplied by C, that is the concentration of the solute coming out in the stream, that is equal to V dC by dt, that is the accumulation inside the vessel. V is the volume of the vessel, dC by dt is the change in concentration as a function of time. At t equal to 0, your C is equal to C naught. Okay, you are injected at t equal to 0 a pulse. Okay, so, this is a first order differential equation, the initial conditions are given, you must have studied long time back in your first year undergraduate program. So, we can solve this first we can integrate this, it will end up with logarithm of c ln c is equal to t q by v plus a constant, and the constant can be estimated using the initial condition. So, you end up with c is equal to c naught e power minus q t by v. Okay. So, if you bring c naught here, it will be c is equal to c naught e power minus q t by v. So, the concentration leaving the tank or the concentration inside the tank will be exponentially decaying. At t equal to 0, the concentration will be c naught, and with time it will be exponentially decaying. So, if you have one single tank and you are injecting a pulse with a concentration of c naught at time equal to 0, so as a function of time, that concentration of that solute will decay like this, and same thing will happen to the exit stream. The concentration in the exit stream at time equal to 0 will be c naught, and then it will start decaying in an exponential manner here, okay, as given by this equation. Now, V by Q, that is volume by flow rate, is called the residence time tau. Okay. So, we can have the equation as C is equal to C naught exponent minus T by tau. Tau is the residence time. Okay. This is a first order relationship for a stirred tank. Now, we can have another situation, okay, where K is infinity. That means there is complete mixing here, okay, complete mixing. K is infinity, that means whatever, there is no resistance at all offered for mass transfer. So, in that case we can assume the whole system as one single tank with volume V plus V dash. Do you understand? So, if K is equal to infinity, there is absolutely no resistance for the movement of the solute. Okay. So, this can be considered as a single big tank with volume V plus V dash. So, we do the same thing, but in this case the volume will become V plus V dash, whereas in the previous case the volume was V. Okay. So, we do the same thing. So, you will end up with the equation like C by C naught equal to e power minus q t by V plus V dash. So, the residence time here will be V plus V dash by Q. So, in the previous case the residence time was V by Q, whereas when K is equal to infinity, the residence time will be V plus V dash by Q. That means the residence time has increased. Do you understand? So, how will it decay? It will decay much slower because your residence time has increased, whereas in the previous case when K equal to 0, residence time is shorter. So, the decaying is faster. When the residence time has increased and K is equal to infinity, it will decay slower. Okay. So, for all other values of K, lying between 0 to infinity, the way it will fall when you give a pulse will be between these two limiting curves. Okay. So, this curve relates to K equal to 0, that means the second tank is completely not used, we do not have to use in the calculation. When K is equal to infinity, there is absolutely no mass transfer resistance. So, it is like one single tank. So, the residence time has increased, okay, and these are the two limits. For any value of K, you will have a curve lying between these two. Okay. Okay, let us again look at the chromatography. So, imagine a 100 liter packed column, okay, the void fraction is 0.3, the equilibrium constant K is given by 13. Now, you are asked to calculate what will be the V, that is how much of the liquid I need to collect, and so that the peak reaches its maximum, that is equivalent to your residence time, okay, because T naught is your residence time and T naught Q is equal to V. So, you need to use the same equation. You remember this equation? So, T naught is the residence time, Q is the flow rate. So, T naught Q will be the V, epsilon is given as 0.3, K is given as 13, volume of the column is given as 100. So, simple. Okay. So, you need to calculate T naught Q, very simple. So, when you do that, you get 940 liters. Okay. So, you need to collect 940 liters of the liquid for it to reach the peak, and if I know the flow rate, I can calculate T naught, that is the residence time. Okay. Simple. So, you need to use this equation to calculate the total volume of the eluate at which the peak occurs. So, we are again using the same equation. So, let us look at another equation. Okay. Now, you have a peak here at 190 minutes and the concentration is 0.0152, that is C naught is 0.0152, T naught is 190 minutes. Now, at the 170th minute you have a concentration of 0.0063. Okay. Okay. So, concentration along this will be less than 0.0152, right. Now, the question is what is the yield at 200th minute. So, here what is the yield, that means how much of this material I have collected at 200 minutes. So, the equation which you need to use is slightly different. So, you are now looking at the original equation which describes this type of Gaussian distribution, C is equal to C naught exponent T by T naught minus 1 divided by 2 sigma square. Okay. So, all I need to calculate is the sigma, because I know the T naught is 190 minutes, I know the C naught which is 0.0152, at T equal to 170 I know the concentration 0.0063. So, I can calculate the sigma. Once I calculate the sigma, I can calculate the yield. If you remember error function, so using that error function equation I can calculate the yield. Okay. Let us go step by step. First let us calculate sigma. Okay. Same equation. So, I know C and I know T naught which is 190 minutes and I know C naught which is 1.0152, I know concentration C which is 0.0063 at 174th minute. So, from there I can calculate sigma. Okay. That is the first step, I calculate sigma, because I know T naught, I know C naught, I know at some time T what is the concentration C. So, I use this equation to calculate my sigma. Now, the next step is to calculate the yield. Okay. Now, I need to go to this equation. If you remember this, so if I collect sample from the beginning right up to 200th minute, what will be the yield? The equation is half multiplied by 1 plus error function T by T naught minus 1 by divided by square root of 2 sigma. Now, I know T, okay, T it is 200 minutes. So, I am collecting the output from the chromatographic column up to 200 minute and T naught is 190 minute, sigma is known. So, I need to calculate the yield. Only hang up is error function and I once showed you the table. Using the table I can calculate the yield. Okay. Now, let us substitute the terms, T naught as 190, T as 200, sigma as 0.063. Okay. When I do that, I will get error function of 200 by 190 minus 1 divided by square root of 2.063. So, I get some number. Okay. I need to determine what is the error function. Like I said, if I know x, I can calculate error of x. This table is very useful. So, if I know x, I will need to calculate what is the error of x. Okay. So, I have 200 divided by 190 minus 1 divided by square root of 2 sigma. So, when I do that, okay, so 200 divided by 190 minus 1 divided by square root of 2.063. So, I will get this x value here and from the table I will get error f x. So, I will get yield as 80%. Okay. So, 80% of the solute could be collected if I collect sample up to 200 minutes when the retention time is 190 and the sigma is 0.063. How did I calculate sigma? I got that from the other concentration at certain time. Okay. So, it is a very useful equation. Okay. This is a very useful equation. So, we saw two very useful equation, one equation relating the concentration as a function of time assuming a Gaussian distribution, and then this is the yield relationship where when I collect the sample for certain period of time, how much of the solute I will be collecting. Okay. This. So, the main assumption in all these is that the curve which we get is a normally distributed output. Okay. Let us look at another problem slightly more complicated. So, you have the product P and you also have an impurity I. Okay. So, you have the product and generally these impurities overlap. Life is not so easy that the product peak and the impurity peak are far away, that whatever you collect will be 100% pure, no. So, if you are collecting sample up to this, there will not be any impurity, but if you are collecting beyond this, some impurity will keep coming. You see this, okay? And you cannot just collect up to this because your yield of the product will be low. So, you need to strike a balance. If I want more of the product, that means if I collect up to this time, then I will have this much of impurity. If I collect up to this, I will have 0 impurity. If I collect up to this, I will have more of impurity. Okay. So, that is what will happen, and these data gives you how these things work. For example, the retention time for the product is 6.42 hours, the retention time for the impurity is 7.6 hours, at a time equal to 6.42, product is 82% and the impurity is 0%, at 7.6 product is 28%, impurity is 43%, at 7, that is here, product is 63%, the impurity is 0.04%, 0.014%. So, depending upon where up to what time I collect, the amount of impurity also will keep increasing, but then if it is a very important product, I would like to collect as much as possible. I might not like to stop with 82% because I am losing 18% of the product. So, I need to collect more of the product, but impurity will also keep going up. So, how do we do this problem? We have to again use the error function type of things. Okay. So, first we use this for the product, T naught will be equal to 6.42 hours, okay, and C naught will be 82, whereas for the impurity T naught will be 7.6 hours and the corresponding C naught will be 43. Okay. So, we have two equations, we will have two sigmas, and then from there we calculate the yield, we calculate the purity, okay, depending upon whatever time I want to collect. Okay. Okay. So, yield is given by this. If I am collecting sample from T dash up to T time, then yield will be given by this. So, you have two error function terms here, and then the purity of solute I, here we have solute and the impurity. So, this is related to the solute, and then the denominator will have two terms, the solute related terms, that is C naught into yield plus C naught into yield for the product. Okay. So, if the yield increases, purity goes down because the impurity also starts coming in. So, if the yield increases, purity goes down. So, it depends on if it is a very expensive product, you would like to increase the yield, but purity will go down, but does not matter, we may have another purification chromatography and try to purify it further. So, if the product is not very expensive, you may like to stop with the lesser yield, but higher purity. Okay. So, that is what you need to do in this particular problem actually, do you understand, and that is what we can do that. Continuous packed column. Okay. So, if one considers a continuous packed column model for your chromatography, because the chromatographic column is continuously packed. Okay. So, the concentration will vary as a distance z, the concentration will vary as a time t. So, general equation will look like this, okay, epsilon dC by dt, okay, that is the concentration of the solute in the mobile phase, dq by dt, that is the concentration of the solute in the stationary phase or solid phase. Epsilon is the void. So, 1 minus epsilon will be the packing material, d is the diffusion coefficient or dispersion coefficient, v is the velocity, superficial velocity. So, you have dc by dz, d square c by dz square. So, this term comes because of Fick's law of diffusion, this term comes because of the movement of the solute because of the superficial velocity, this term comes because of the accumulation in the mobile phase, this term comes because of the accumulation in the stationary phase. Okay. So, these equations cannot be easily solved analytically, so we need to use numerical solutions and we need to have some idea about the diffusion coefficients and so on actually. Okay, that is how we need to do. So, if one assumes that the diffusion or dispersion is negligible and accumulation in the void space dC by dZ is also negligible, then the equation will go up to be a very simple form. That means we neglect diffusion coefficient and then we also neglect the accumulation of the solute in the void space, that is dC by Z. So, we will end up with 1 minus epsilon dq by dt is equal to V is the velocity, dC by dZ is the change of concentration along the distance, and this is the accumulation in the solid phase or the stationary phase as a function of time. So, the initial condition, there is no solute adsorbed in the packing before injection. Obviously, at time less than 0 everywhere there is no solute at all. So, at time less than 0 Q's will be equal to 0. At time equal to 0 you are injecting a sample, the solute is just entering the bed, okay, at time equal to 0, and that is what you are doing actually. For solving this equation one needs a relationship between Q and C, okay. So, between Q and C, so you can have a linear adsorption, you can have non-linear, you can have a Freundlich, Langmuir and so on actually. Then you also have to have controlling factors, okay, if there is a mass transfer from the bulk of the solution to the surface of the particle, because the solute has to move from the bulk of the solution come to the surface of the stationary phase and get adsorbed. Then there could be a diffusion inside the pores of the adsorbent. If the pores are very porous, then there could be diffusion. Okay. Then if there is a reaction, then of course you will also have a reaction, but in chromatography we are not talking about reaction. So, we can completely ignore this. So, two things can happen. One is the mass transfer of the solute from the bulk solution to the surface of the particle, and then diffusion inside the pores, that is called the pore diffusion, okay, especially for example in gas, if you have the gel permeation chromatography where the solutes diffuse inside the pores, this term may become important also. Okay. Okay, so if the mass transfer of the solute from the bulk to the surface of the particle is controlling, that means concentration in the bulk could be C, but concentration on the surface could be C star, then C star and Q will be in equilibrium, not C and Q, C star. So, you need to remember C star and Q will be in equilibrium, not C and Q. Okay, then your equation could be 1 minus epsilon dq by dt, that is concentration of the solute on the stationary phase as a function of time. This will be equal to KLA, KL is the mass transfer coefficient, A is the packing area per volume, C minus C star, this is the driving force. So, you see that C star is the concentration in the solution which could be in equilibrium with the Q. So, the relationship between Q and C star could be linear or non-linear, but not between Q and C. So, between C and C star will be based on the mass transfer. So, this is the equation, and we can substitute for C star in terms of Q if you know what type of adsorption taking place. Okay. So, if it is like if you remember linear, Q could be equal to K C star. So, we can replace C star with okay, Q by K. Okay. So, if you replace, you can have changes in the standard deviation. If you look at if you remember the equation for C in terms of C naught and T naught, you also have a sigma coming in, and the standard deviation I said is sigma into T naught. So, the sigma could be dependent on so many of these terms like your mass transfer coefficient, the area per volume and so on actually. So, the standard deviation will be affected depending upon the type of mechanism. For example, sigma square could be the velocity KLA, that is the overall mass transfer coefficient and length of the column. Okay. Area per volume, okay, is given by A is equal to F dash divided by D into 1 minus epsilon. F dash is 6 for a spherical particle and it is equal to 4 for long cylinders actually, and d is the diameter of the spherical particle. Okay. So, A is generally of this equation, if you assume spherical, then this will become 6, for long cylindrical this could become 4. So, decreasing particle size increases mass transfer coefficient, okay, because A comes in the denominator. Increasing velocity and particle size, okay, increases sigma and hence increases the width of the pulse. So, if I increase velocity and if I increase particle size, sigma becomes larger, okay. If I increase velocity and if I increase and particle size, it increases sigma and hence increases the width of the pulse. Increases column length, decreases the width, okay. So, if I have a longer column, I may be having a smaller standard deviation. If I am decreasing particle size, I am increasing mass transfer coefficient. Increasing velocity increases sigma, increasing particle size increases sigma, because my mass transfer coefficient decreases there. So, the standard deviation changes because of dispersion of flow in the column due to polydispersed packing material. So, although I say the particle size is say d, but then you will never have a very uniform particle size. The particle size may be having a small distribution. So, because of that polydispersed nature, the standard deviation could be also changing actually. So, standard deviation is never a constant, but it could be a small distribution because depending upon the polydispersed nature of the packing material. So, changes in standard deviation depends on the type of mechanism. Is it pore diffusion, is it bulk mass transfer like I showed you, and it depends on the number of stages also. Generally the number of stages or number of plates, it is an ideal, but it is never ideal because the distribution of the solute coming out of the column never follows a normal or a Gaussian or a bell shaped distribution. So, all these reasons affect your standard deviation. So, all these reasons affect your calculations. So, you have to, but these equations are very important because they help you to get some feel about the purity, yield, the number of stages. We can use it for comparing two different columns. We can even simulate some output peaks and so on actually. So, changes in standard deviation, like I said, these are very useful equations to have actually. Okay. So, we have an equation, for example, standard deviation as you know is T naught sigma, and that is equal to 12 minutes, and the retention time is 93 minutes. So, what will be the time if I want to have a 90% yield? So, we can do that calculation, okay, not difficult to do. Okay. Yield, you remember this equation I showed you a few minutes back, half into error function T by T naught minus 1 divided by square root of 2 sigma. So, I know T naught, okay, 93 minutes, I know T naught sigma 12 minutes. So, I can calculate sigma. So, I can substitute all these. So, I am running up to some time, so that my yield is 90%. So, I need to know what should be my time, simple, okay, very simple. I can substitute and then I can use error function to do the calculation, and yield if I am collecting. So, this equation boils down if I am collecting from 0 time to this. So, if I am collecting from T dash to T, this is the equation, but if I am collecting from 0 time, okay, the equation will boil down to this. So, from 0 time what should be my T to get a 90% yield. So, I know T naught is 93 minutes, sigma can be calculated from here because T naught sigma is 12 minutes, I substitute here, okay. So, I will get a error of x as I showed you before from the table. When I know x, I can calculate what is the error of x, and I can get the T. Okay. So, 93 sigma is equal to 12 minutes. So, sigma is 0.0129. So, I substitute here. So, that will be error of x. So, yield is given by 90 minutes. So, what should be the time? 115 minutes. So, if I start collecting sample from 0 to 115 minutes, I will be able to collect 90% of the sample. Okay. You see this is a very useful type of calculations in chromatography. So, because you need to know how long I need to collect for getting a 90% of the solute or 95% of the solute, knowing certain data, knowing things like standard deviation, knowing things like retention time and so on actually, because otherwise you will be just collecting too long and there could be impurity peaks coming downstream which may be getting added up. Okay. And these type of calculations are very useful even when you are going in large scale industrial scale plants. And of course, there are some assumptions which are the underlying in this calculations, and you cannot help them, but these equations are very useful for you to use. Okay. So, T is 115 minutes. So, initial mobile phase velocity is 30 centimeter per hour and it is doubled. So, to achieve 90% yield, how long it will wait? Now, the process is controlled by internal diffusion. So, the process is controlled by internal diffusion, then sigma square is getting affected. Sigma square is proportional to V velocity, d square particle diameter divided by L. Okay. So, the velocity is doubled. Okay, the velocity is doubled. So, your sigma square is going to be square root of that doubled term. So, obviously, the sigma is getting bigger. Okay. So, obviously, your dispersion is bigger. So, velocity is doubled, then T naught is reduced by half, that is T naught is equal to 93 by 246.5. Okay. Then the sigma square is equal to V d square by L. So, velocity is doubled. Okay. Your velocity and sigma are related by this relationship. So, your sigma will become 0.182. Okay. So, your standard deviation, okay. So, sigma will become here, your T naught has reduced. So, I need to use this equation to calculate the T, which comes out to be 61.8 minutes. So, to get the same 90% yield, when I doubled my velocity, okay, when I doubled my velocity, my retention time decreased by half, my sigma changed in this fashion, that is square root. So, I will get a new sigma. So, I will get a new T naught, it became 46.5. So, when I substitute and then I calculate, now it has become 61.8 minutes. Okay. So, to get a initial mobile phase is 30 centimeter per hour, and when I doubled it to achieve the 90% yield, my T naught reduced from 93 minutes to 46.5 minutes. My sigma changed quite a lot, became 0.182 minutes, and then I need to wait 61.8 minutes to collect 90% of my solute actually. Now, the process is controlled by external mass transfer. Okay. Previous case it was a pore diffusion. Then the equation for sigma square is like this. Okay. Please note the equation changes between the previous and this one. Here there is a change in the diameter raised to the power 3 by 2. Okay. So, the velocity diameter of the particle. So, sigma will become square root of V raised to the power 1 by 4, whereas if it is pore diffusion it is V raised to the power half. So, your sigma has changed to 0.153, whereas in the previous case it was like 0.18. Okay. So, T becomes 59.4 minutes. So, you see that if it is a internal pore diffusion, you have different sigma, but your retention time is same of course when you double the velocity, but the sigma has changed. When the process is controlled by external mass transfer, your sigma is a function of V raised to the power 1 by 4. So, you get a new sigma. So, the time required to collect is 59.4 minutes. So, depending upon the type of mechanism, whether it is external mass transfer, bulk to surface is controlling, or the pore diffusion is controlling, you are going to have different sigma values. So, you will have different collection time to achieve 90% yield. Okay. Very interesting problem these are, and they are very practical problem. So, if the process is a set of ideal equilibrium stages, okay, sigma square will be unchanged, okay, because sigma square will be function of only the length of the column. If you remember, number of stages will be directly proportional to the length of the column. So, T naught is reduced by half, but sigma square will be unchanged. So, when you do that, then T becomes 57.5 minutes. Okay. So, we looked at 3 different situations. Okay. We looked at 3 situations where one is the bulk mass transfer is controlling, the second one is the pore diffusion is controlling, third one is ideal set of stages. So, when we do these 3 different situations, so when I double the velocity through my chromatographic column, my retention time goes by half, but the sigma changes depending upon the type of mechanism. So, my collection time changes for each of these cases to achieve 90% yield. So, we looked at chromatography in very detail in the past 4 lectures. We looked at various principles involved in it, and then we also looked at the mechanisms of these different types of chromatography, and we did a large number of problems which connect the various principles of chromatography, which are very useful for scale up, which are very useful in industrial applications as well. Thank you very much.